Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Haikal bin Ikhlas ini. So today our group gonna presenting about communication principle assignment 3 passcode modulation. So before we go any further, allow me to introduce my teammate, which is Farhan, Hakimi, Hasif, and also Fakhrullah. So the content for our assignment is introduction, exemplary right, question 1, question 2, question 3, discussion, and also conclusion. So for the introduction, passcode modulation or PCM is a digital technique that involves sampling an analog signal at regular intervals and coding the measured amplitude into a series of binary values transmitted by modulation of a pulse or intermittent carrier. It is the standard technique in telecommunication transmission.
Assalamualaikum. My name is Muhammad Hakimi. I will show how to use MATLAB Simulink to apply the pulse code modulation. For example 1, we use MATLAB to simulate the signal quantization. This is our input, a sinusoidal wave with a frequency of 1 Hz. The sample signal is produced by the dot product between the sine wave and square wave. So this is the output. This is the original signal. This is the sample signal. This is the square wave that we use to produce the sample signal. This is the signal after decoding and encoding. Then, we use Simulink to replicate the code to produce the same output. We use sine wave function block and pulse generator block to generate the input signal. We use dot product block to generate sample signal. Then we use uniform encoder and decoder block. Lastly, we use scope to plot the waveform. So this is our output for the analog signal, square wave, sample signal, encoded and decoded. If we compare with the MATLAB output, it generates the similar output. For example 2, we study the effect of compending or compressing on signal quantization. We can see from the output here, the compended signal gives more accurate signal quantization. For Simulink equivalent, we use sine wave, log and divide to generate our input signal. Then, we apply compression using mu log compression block, connected to uniform encoder and decoder, and then connected to the expander. For quantization without compression, we only connect to encoder and decoder. Lastly, we connect to the scope to show the output. As we can see here, it generates the same output with the MATLAB output.
Okay, now I will be presenting about the 3.1 exercise, question 1. So the question 1 is, what is the frequency of the analog signal that has been used in the example 1? So the example is referring to the code written in MATLAB. So see, this is the snippet of it. In the MATLAB code, there are a line code that are written as A equal to sine, parenthesis 2 times pi times t. So this line represents analog signal equation. So we can compare this analog signal equation to the general equation of the sine wave, since the analog signal equation does represent the sine wave. So if we compare with the general equation of sine wave, is the general equation of sine wave is y equal to a, which stands for amplitude, sine angular velocity times time within the argument inside the sine trigonal function. So angular velocity is equal to 2 pi times the frequency. So if we compare the 2 pi times the frequency, you can see that 2 pi is like literally identical. So we can 2 pi is same as the angular velocity and the time. So if you compare, there are actually 1 is hidden within the trigonal argument, which is the frequency, which is, we can conclude that the frequency is 1. So it's fill the representation of the equation.
Hello everyone. So today I will be explaining to you guys about the calculation of SQ and R calculation. So the signal to quantization noise ratio, SQ and R, is a ratio that measures how well the signal is represented compared to the errors introduced by the quantization process. We start the calculation with the SQ and R formula, which is 20 log 10 of 2 power by n times square root 3 over 2. Then we split the equation by the indices to make our calculation easier. Then we conclude the final equation of SQ and R is 6.02 and plus 1.7689. Given in the question is the n equal to 8 and n equal to 16, which is the number of bits in digital representation. So we have to change the number into bits representation, which give us the value of n equal to 3 and n equal to 4 respectively. From the numbers given, we can just substitute the n with the given value. Therefore, the signal and quantization noise ratio can be obtained. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Fakhrullah. Today I'm going to show you how to use the MATLAB simulator for the questions 1 and question 2. First, put a function generator, a signal generator. Make sure the amplitude is 1, the frequency is 1, and hertz using unit hertz. Then put a pulse generator. The period is 1/10 and the pulse width is 50. Then put a dot product. After that, use a uniform encoder. Make sure that is bit 1 and bit 3. Put a uniform decoder. Bit 1 and bit 3, the same as uniform encoder. Then put the scope. Connect all the this in one line and make sure you have all the scope. Then we can run it. The result is similar to the example 1. For example 2, put a sine wave plug and then connect it to device, and then uniform encoder, decoder, and connect it to a scope. For sine wave, make sure it has 0.05 amplitude and the frequency is 20. Log is 10 decimation. For encoder is the same as the example 1, bit 1 and 3 bits. And for decoder, bit 1 and 3 bits too. They connect to the scope. For the next one, sine wave clock connected to a device 1. After that, connected to the molar compressor, uniform encoder, uniform decoder, mu-law expander, and to the scope. For the sine wave, show the amplitude is 0.05 and frequency is 20. Decimation is 10. The molar compressor is 255 mu value and the peak is 1. On the encoder is peak 1 and peak 3. And for decoder, peak 1 and bit 3. Molar expander is the same as molar compressor, 255 mu value and peak signal is 1. And then run it. This is the result. It's very similar to the example 2.
Okay, now I will be presenting the discussion assignment, discussion section of the assignment, the pulse modulation through the optical result. For the example 1, you can see that the input and output and the simulating output is the same for the square signal. So for the pulse modulation, the square signal will be combined with the analog signal. Will combine to generate the sample signal. As you can see, for both analog signal and sample signal, compare is the same with the MATLAB simulator, and the input and the simulating output is the same. It's almost it is identical. Then later, the sample signal will then go through the encoder process, and the encoder process, you can see the MATLAB code output and the MATLAB simulating output is the same. Then the value is ranging from 0 and above, and same as the encoded MATLAB simulation, like 0 and above. And then this encoded signal will then be decoded through the process of decoding the decoder by the encoder. So as you can see, the signals that is being decoded into the values amplitude ranging from 1 to -0. The output is also same. The output is same for both code and CA for the discussion for example 2. So by using the compend, new rule of compend, which is for condition expansion, you can see that the MATLAB code output and MATLAB signal output is identical. So first we'll use C for the signal that using the compend. As you can see that the received signal using the compression expansion is closely, nearly, not perfect, but nearly accurate to the original signal. The value does much more close to the original signal, as well as same as the MATLAB signal output. You can see that the values pretty much the same whether we're using code or the MATLAB signal. However, if the pulse code modulation without using the compend, you can see that the received signal without the compend is like much more inaccurate. It's not very accurate to the original signal. You can see the value is just very simple. The value is very simple and that's not very close to the original signal. So you can see the difference between the method and signal. It's a bit different, but because it's not very accurate, the value is not very accurate. So by using the new law of compression and expansion, we can reduce the noise disturbance so that with compend we can make the signal receive much more accurate and true and more better.
For the conclusion, what we can conclude is, in a nutshell, we are able to design a pulse code modulation and able to understand one of digital modulation technique. Besides that, we also managed to generate the pulse code modulation PCM signal by using MATLAB. Last but not least, we are able to plot the pulse code modulation signal by using MATLAB. So that's all from our group. Thank you.